So let's discuss now how humans regulate body temperature during exercise. This is very crucial to be able to regulate body temperature, especially when we exercise in a hot environment. So we will discuss challenges of exercise in a hot environment and how heat is transferred during exercise. And also use some brief calculations just to get an idea how you can do some of those calculations of heat gain and heat loss. What is really interesting is that humans, as endotherms, they're able to survive in a very large variation of temperatures. So for example, in this diagram here, you can see that the human body actually is able to regulate body temperature very, very tightly, like right around here, around 37 degrees Celsius or 98.6 Fahrenheit. And usually we can survive in between this fairly small range between 31 to 41 degrees Celsius, so somewhere between 86 to 104, 5, 6 maybe degrees Fahrenheit, and potentially can avoid death or escape death in that range. However, we can live in a very environment of very large range, from very, very cold temperatures well below minus 50 degrees Celsius, minus 60 at some point in the poles, all the way to extremely high temperatures in the desert. And I know in Phoenix, where I live, the temperature quite often surpasses the 44, 45, 46, maybe sometimes degrees Celsius, and the temperature of the sun quite often in many places in the world, it might be even above 60 something degrees Celsius. The black tarmac under sunlight in the middle of the summer in some places in the world could be close to 70 degrees Celsius. So let's discuss the heat production as a response to surviving, so living at rest or during exercise. So our whole body oxygen uptake at rest is around 3.5 ml per kilogram body weight per minute, which is the definition of one metabolic equivalent, or 1 met. Or during exercise, it can increase, of course, depending on the intensity of exercise. So going from rest from 3.5, quite often you can exceed the 70 ml per kg per minute. Of course, if you're somebody who can exercise in very high intensity, like an endurance athlete, like a marathon runner or a cyclist. In the literature, there are people that have been recorded with oxygen uptake exceeding the 80 ml per kilogram per minute. Actually, I have measured people that they were like very low 80s. So that as a response, at rest, we burn approximately 1 calorie per minute. Of course, depends on your body weight. And during exercise, then that thing can go, like, obviously you can burn as many as 20, 25, or even 30 calories per minute, depends on how endurance trained you are and of course your body size. If we look at body heat production, so during intense exercise, body core temperature can increase as fast as 1 degree of Celsius per minute. So if we didn't have a system that we could regulate body temperature, within 3 to 5 minutes, internal body temperature will increase so fast that we will reach fatigue associated with hyperthermia, or increase in body temperature. There are experiments that they have shown during intense cycling exercise, muscle temperature can increase by approximately 1 degree Celsius per minute. This is very, very high intensity exercise, and measuring local temperature in the quadricep muscles, where most of the metabolic exchange is happening during cycling exercise. So let me show you one example. And of course, this is a rare case, but just to get an idea what it means in a combination of a thermoregulatory system that did not work appropriately in combination with high environmental stress. This is the story of Mark Doherty, also known in the literature as the Meltdown Man, an Australian man where he tried to run a 5-mile race in 1988. The temperature that day was 38 degrees Celsius, and it was so hot that the organizing committee, they decided to postpone the race. However, he decided to, since he was there already, he said, I will do my 5-mile run regardless of whether the race will take place or not. Unfortunately, a little bit before the completion of the 5 miles, he collapsed. He was taken to the hospital. His core temperature was over 42 degrees Celsius. They had to do a tracheotomy to allow him to breathe. His immune system collapsed. He developed renal failure. Within 24 hours, his left leg turned into khaki green with the texture of boiled meat. And these are words that I took out of the paper that was published that they are referring to his case. And 27 days later, his leg had to be amputated and he remained in coma for 132 days. This is, of course, a terrible case, and this is not something that will happen to you if you decide to do any type of activity in a hot environment. But this is a great example to get an idea what it means to exercise in a hot environment when the environmental temperature does not allow you to eliminate so much heat, and also when you do high intensity exercise that produces a lot of internal heat. So let's discuss a little bit the overall how the system works, how we thermoregulate. So when we produce heat, let's take the example of exercise, exercise will lead an increase in body temperature. So our muscles locally will start increasing in temperature, and blood will start picking up the heat and distribute the heat all over the body. That increase in temperature will stimulate the hypothalamus, which is the center or the thermostat of the human body, the center where internal body temperature is sensed. As a response, we get the first response, which is called vasodilation. So we increase the blood flow to the skin, so that allows to transfer heat from the deeper areas of our body, from the muscles and from different tissues all the way to the skin. And then from the skin, we can dissipate that heat towards the environment. We also produce sweat. So sweat is produced from the sweat glands, and that wetness in the skin helps to increase evaporation. So evaporation of sweat from the skin is what releases heat to the environment. And hopefully as a response, the temperature, after we stop exercising, the temperature will return down to pre-exercise normal body temperature value, which is around 37 degrees Celsius. So this is what happens when everything works correctly. This is a case of one of the subjects actually that participated in one of my experiments actually a few years ago. And this temperature right here, 39.5 degrees Celsius, is his internal body temperature. That gentleman actually who had volunteered for a study, as you can see, he's very red. His face is very red as a response to skin vasodilation. So very briefly, let's discuss what happened in cold. So when body temperature goes down, we have again a signal to hypothalamus. And now instead of vasodilation, we have the opposite effect. We have vasoconstriction. So we're trying to decrease the amount of blood sent to the skin. So that way we thermal insulate our body and we decrease the amount of heat that will be released towards the environment. So that's why our extremities get cold. And if you look at them, they usually get a little bit whiter. So the blood goes away and the color of the skin changes and gets a little bit lighter in color. So this is a protective mechanism to try to conserve as much heat as possible in the body. The second step, when the body temperature starts decreasing significantly, then we get tremor or shivering. And what shivering is actually involuntary muscle contractions. And as the muscle contracts involuntarily and we start shivering, that generates heat. And that increase in heat will help us to regulate body temperature, and that extra heat can help us to increase a little bit our body temperature. Of course, if the environment is extremely cold, that shivering is not going to last forever, and we won't be able to keep shivering and produce enough heat to regulate body temperature. So unless we can warm up a little bit or stay away, unfortunately, the body temperature will keep decreasing to the extent that we won't be able to survive. So let's talk now about what are the biophysical mechanisms through which heat is dissipated from the body. And there are 4 of those. Let's start from the first one, which is called conduction. So conduction, remember the word contact. So conduction refers when 2 objects with different temperatures, they get in contact, and then we have heat transfer from the warmer body to the colder body. So a good example of conduction is, I don't know how many times you have been to a football stadium when it's that cold, potentially even snowy, and then you sit in the bleachers or in those plastic or aluminum sometimes seats, and then you are getting cold because what you're trying to do, your body's trying to warm up the seat via conduction. So you're transferring heat from your warm body to the cold seat, and you're warming up pretty much the bleachers of the stadium with your body heat. This is an example of conduction, transferring heat through direct contact. So another way of heat transfer is what we call convection. And convection is when we have motion of gas or liquid across objects. So an example of that would be like having airflow. So air molecules, we sit in front of a fan, and that airflow can help increase heat loss via convection, or being in cold water, like being immersed in water and swimming in water. The cold water that passes through the skin transfers heat from the skin to the water, or from the skin to the air by convection. One pre-requirement to have heat loss via convection is that your skin temperature is supposed to be warmer than the environment. So let's say skin temperature at normal conditions, it could be, let's say, around 30, 32, 33 degrees Celsius, when the environment outside is in the 70s or even 80s, and it's cooler than the skin. So a fan, for example, can help to have heat loss via convection. If the temperature of the air is equal to the temperature of the skin, then we cannot lose any heat via convection. And then the worst case scenario, when the environmental temperature is much higher than the skin temperature, then instead of losing heat, what we do, we gain heat. So, how come a fan feels good even if the temperature is above our skin temperature? So a case where the temperature could be in the 40s, like over 100 degrees Fahrenheit, and it blows, then it still makes us feel a little bit better versus when we don't have any airflow. And yes, it makes sense. And yes, we don't lose heat via convection, and we might even gain heat via convection because the air is warmer than our skin. But on the other side, what the fan or the airflow can help speed up evaporation, which is another way that we can lose heat. Convection also can speed up the heat loss in the winter when the temperatures are low. And in this example, it presents what is called the chill factor, the wind chill factor. So let's take an environmental temperature down here. So let's take, for example, 0 degrees Celsius, so 32 degrees Fahrenheit. When the temperature is 0 degree Celsius, freezing, and the wind speed is 0, this line indicates the wind speed, then that temperature feels cool, but not extremely cold. If we go up here where the wind temperature is significantly higher, so we have, let's say, 45 miles an hour speed, very high speed, the same exact temperature can give the impression of bitterly cold, even though the true temperature, the ambient temperature, what we call, is exactly the same. So what's the difference? The difference is that the wind speed will speed up the process of heat loss by convection, and as a response, our skin will chill down quickly, and we will feel much colder. So this is a factor that plays a role when we see the temperature sometimes in different temperature or weather apps, and they say temperature is X, but it feels like Y. So it could feel much warmer or much colder, it depends on the wind. So let's move to the next mechanism, which is called heat loss by radiation. And radiation is when we lose heat via electromagnetic fields. Actually, not always lose, it could be either losing or gaining. So if we take the example of the summer, a classic example of radiating heat gain is when we're exposed to solar radiation. So when we have direct contact visual contact between the sun and our body, for example, when we're exposed to the sunlight, we gain heat from a very warm object, which is the sun, and thanks that is super, super far away, so that distance is that what allow us to survive on planet Earth. Versus when we're in an environment that everything around us, it's very cold, like being around an area with a lot of snow, for example, or ice, and then we will have a lot of heat loss. So heat exchange via radiation, it happens through electromagnetic waves, and it happens between two objects that they have different temperature. So a classic example that I like to use sometimes is like when we are close to a fireplace, and the side, let's say we have a fireplace on one side of our face, the side that is in direct optical contact with the fireplace, it can get super, super hot, even though the ambient temperature in that room, it's about the same everywhere around the room. So this is the concept of heat exchange via radiation. And the last, and actually not the least, but rather the most important way of heat exchange, especially during exercise, is sweating, or actually, to be more precise, evaporation of sweat. When sweat gets evaporated, this is the most efficient way to really release heat towards the environment. So, we all know that we sweat when we're in a hot environment, and I know for many people it's a very unpleasant experience. I don't think anybody's excited to sweat. But on the other side, sweating is a way that our body can dissipate heat to the environment. So it's a protective mechanism. It's the single most effective way to dissipate heat. So is there a situation where sweating is not effective? And the answer is yes. There are situations where sweating is not that effective, and this is when the environmental humidity is very high. So if you're in the tropics, so somewhere that environmental humidity is above 60, 70, 80%, then thermodynamically, the water droplets from the skin are dripping, but they cannot be evaporated, at least effectively. So as a response, the heat dissipation through evaporation is really limited or almost down to suppressed, depends how high the humidity is. Another question that I get quite often: what happened during swimming? Do we sweat in the water during swimming? And the answer is yes, we sweat, but obviously, as you can understand, we cannot evaporate sweat in the water. And because, at least in the swimming pools, where the temperature of the water is regulated to be a little bit chillier than a hot tub, the other mechanism, so convection, is more effective in dissipating heat versus evaporation. We don't really evaporate much because we're in the water. Our sweat glands cannot, the wetness on the skin cannot be evaporated because we're underwater. So yes, we sweat in swimming, not as much as we will sweat outside of the water. But unfortunately, we cannot evaporate the sweat, so we don't really get any benefit from that sweat that it is produced. So let's walk through some examples of what happens in different environmental temperature and humidity and situations. And I have this example of a cyclist and trying to think what is happening at the same time while somebody cycles outdoors. So we have multiple things that are happening. First of all, we have what is called the metabolic heat production. So because of the intense exercise, the body produces heat, and that heat needs to be dissipated to the environment. Otherwise, internal body temperature will keep rising and rising and rising to the extent that your body will not be able to sustain not only exercise, but not even surviving in this internal body temperature. So metabolic heat is something that increases body temperature. And of course, we can have increase in body temperature via other environments like solar radiation. If it is a sunny day, we can gain heat through the sun. Also, we can have radiation by reflection from the tarmac. So the floor, especially in the summer, the temperature of the roads can be very high during intense summer temperatures and high solar exposure, and that high temperature of the floor can also contribute to increase in body temperature on the cyclist. And pretty much all the objects around the road in the middle of the summer tend to be much higher than the skin temperature. So instead of losing, you gain heat from the sun, you gain heat from the hot objects like the road, and you gain heat through metabolism, metabolic heat production. So you can lose heat by convection, and convection will work only when the air temperature is cooler than the skin temperature. We have heat loss by evaporation of sweat. So you sweat a lot, and the fact that you're moving fast into the air, that helps to speed up the process of evaporation. And as far as conduction, we don't have too many objects that are directly touching the cyclist outside of the saddle, maybe the grip of the handle. So you don't really have massive temperature exchange between objects that the cyclist is touching. So I would say it's pretty safe to say that heat exchange via conduction is limited, or almost, let's say, practically zero. Let's talk now about some very specific examples. So look up here in this part of the diagram, you will see the environmental conditions. So let's say we have 20 degrees Celsius or 68 degrees Fahrenheit with 20% humidity. So think of the four mechanisms that we discuss: conduction, convection, radiation, and evaporation of sweat. So conduction, let's take we said earlier that the example of cycling, you don't really have much heat exchange through conduction, since the contact between the body and the bicycle is minimum. So let's assume that in all conditions conduction is almost non-existing or not significant. Then let's start by convection. Will convection help to cool down during exercise? And the answer is yes. And it's yes because the environmental temperature, so the air, 20 degrees Celsius or 68 Fahrenheit, it's significantly cooler than the skin. That during exercise, the skin would be around, let's say around 80 something. Usually the skin is around 90 degrees Fahrenheit or 33 degrees Celsius. So the cooler skin compared to the air, the skin will be, the cooler environment compared to the skin, it will facilitate heat loss via convection. How about radiation? If the temperature is cooler than our skin and our body, all the objects around would be also cooler. So via radiation, we will be losing also heat. If it is sunny, we will have some heat gain through the sun. But the last and probably most important component, which is evaporation of sweat, the high speed that you're moving in the air with a bicycle, plus the low environmental humidity, 20% in that case, will really make a big difference in heat loss. So the best pathways for heat dissipation in that case would be sweat evaporation, sweating and sweat evaporation, and heat loss via both radiation and convection. So let's go to another example. Next one. So now we have 33 degrees Celsius, 90 degrees Fahrenheit, with 20% humidity. So much warmer. So 90s, it's still warm, and for Phoenix standards, it's not that super warm actually. But by being 33C, if we take again one by one the mechanisms via convection, we won't have any heat either gain or loss, because approximately this is the temperature of the skin. So to have either gain or loss via convection, you have to have some temperature gradient. So the temperature has to be different between the skin and the air. 33 degrees, it's approximately the temperature of the skin during exercise. So the air, it's about 33 degrees, so we won't have either gain or loss via convection. How about radiation? I think the same will be for radiation, because we assume that everything around will be around the same temperature. We will have some heat gain from solar heat, and if it is sunny for a long time, probably the road will be warmer than 33, even though the air is 33, so we might also gain some heat via radiation. So in that very hot environment, the main pathway for heat dissipation will be evaporation, because it's very dry, 20 degrees C with high speed that facilitates sweat evaporation. Evaporation will do its magic, and that would be the main way that we can really dissipate heat. Let's go to the next environment. So let's go 38 degrees C or 100 degrees Fahrenheit with 20% humidity still. So in that case, we will have, through convection, we will have a heat gain, because now the air is warmer than the skin. So we will be gaining heat from the environment. We will be gaining heat via solar radiation and reflective radiation from the ground and any other objects around. And of course, we will have evaporation of sweat being the main pathway of heat dissipation. So again, the low humidity that in combination with a higher movement that the cyclists are creating during cycling while you're moving in the air, that will facilitate sweat evaporation. So that would be the most effective way to really lose heat, because all the other pathways are increasing heat load. So you're exercising and you produce a lot of heat, You have the high environmental conditions that your body gains heat from the environment via radiation and convection. And sweating and evaporation of sweat is the main pathway. So let's go to another environment. Look again up here, 20 degrees C, 68 Fahrenheit, 90% relative humidity. So in this environment, because of the cool temperature, we will have again heat loss via radiation, at least from the surface around the cyclist. Heat loss via convection because the air is cooler than the skin. However, the 90% relative humidity will create an environment where the athletes will be sweating, but the sweat will not be evaporating very effectively. So the main pathways of heat dissipation in that case will be convection, some radiation. If there is sun, there will be gain from solar radiation, and very small amount of heat dissipation via sweating. So this is it starts getting a quite stressful environment for the cyclist, because sweat evaporation is the single most effective way to dissipate heat. So let's go to another, and this is the last example, where the temperature now is 38, so the temperature is above skin temperature, 100 degrees Fahrenheit with 90% relative humidity. This is what we call, in heat physiology, we call it uncompensable environment. So your body cannot compensate. You're pretty much in such a stressful environment that your body cannot really do much to dissipate heat. So you cannot exercise for too long before your body temperature will go so high that you will risk of creating major heat injuries as a response to exercise. So convection, with convection you will be gaining heat because the environment is warmer than your skin. Through radiation, everything is warmer than the skin, so again you gain heat, and you gain also heat through solar radiation. And because of the very high humidity, the evaporation of sweat will be absolutely minimal. And because of the low sweat evaporation, pretty much none of the mechanisms will really help you to dissipate heat of the environment. So sweating is very limited. Radiation, convection cannot really do much. So this is not a good environment to exercise. This is not safe, and the best advice is not to compete in this kind of environment. We'll talk a little bit later throughout the semester about this paper. This is an interesting study that these authors were trying to make a case that over drinking for this case of a soldier induce what is called exercise-associated hyponatremic encephalopathy at the same time that this person got the heat stroke. And even though he was drinking so much, he ended up dying from hyponatremia and heat stroke together. So they were trying to make a case that no matter how much you drink, in some cases you cannot save yourself. This is a classic case where the environment was extremely stressful to the extent that the subject could not compensate no matter what. So this is the environmental conditions. 37.5 degrees C, very close to the example that we just discussed. Relative humidity 85%. WBGT, which is wet bulb globe temperature. This is an overall temperature taking into consideration humidity and solar radiation. And here we have soldiers that have been walking for many hours while they're carrying like a very heavy load. So they were trying to make a case that even though he was drinking a lot of fluids, this person could not he ended up dying. And the top line, the one that you can see here between the two red lines, is his core temperature that went all the way up to 43 degrees Celsius, and he ended up dying from heat stroke. So a very, very stressful environment. It doesn't matter how much you drink when the environment is stressful beyond compensation. So your body, there is nothing for your body to do to really help you do better and maintain homeostasis at some stage. So overall, I hope you got a good idea what are the four mechanisms with the examples that we discuss. Conduction is by direct contact. Convection, it's via air or via water. Radiation, it's when two objects, they have visual contact, so the two objects can see each other. Think of solar radiation or fireplace. And sweating and specifically evaporation of sweat is the single most effective way to dissipate heat. So during exercise, think a little bit in a very simplified version of your body trying to balance metabolic heat that you produce, environmental heat that sometimes you end up gaining heat from the environment, plus all the mechanisms that could potentially help to dissipate heat in the environment. However, some case, if the air is too warm, if the ambient conditions and the solar radiation is too high, instead of helping you to lose, some of those things might end up contributing to gaining more heat instead of losing. And evaporation, which is primarily driven on environmental humidity. So relative humidity, high relative humidity really limits evaporation. And you keep producing sweat, so you keep losing fluids, you keep getting dehydrated. However, instead of evaporation and heat dissipation, your sweat just drips to the ground without having the benefit. So let's get back to discuss the WBGT temperature that we mentioned earlier. So typically when we talk about environmental temperature, we're referring to what we call ambient temperature or dry temperature or air temperature, which is only one of the factors that influence how our body perceives temperature and how able we are to thermoregulate. So outside of the air temperature, there are two significant factors. One of them is environmental humidity that, we clearly understand that at least living in Arizona, we have the advantage of low humidity most of the year. And the second one is the solar radiation. So this very simplified device that you can see in that screen can provide estimates of the other two temperatures. So one of them, this one right here, the A, refers to the ambient temperature, or what we call also dry bulb temperature. This one, which is actually a thermometer that is connected to a little piece of cloth, and the cloth, but not the thermometer, it's touching the water, so it's constantly wet. And as a response to evaporation, the temperature in this thermometer is supposed to be constantly a little bit lower than the air temperature, assuming that the humidity is less than 100%. And also here it's a black sphere, a globe, where inside that ball there is a thermometer that it measures the temperature as a response to the solar radiation in this black ball that collects a lot of solar heat. So we have been using for many years this temperature, which is called WBGT, which is the acronyms for wet bulb globe temperature. So, and these are the three factors that impact this temperature. So it's the temperature, the dry bulb temperature, which is this one, the first factor. The second one is the wet bulb, so the temperature of this thermometer. And third one is the globe temperature, which is the temperature influenced by the solar radiation. So if we multiply with these factors, 0.1, 0.7, and 0.2, and we add them up, we get the WBGT temperature. It's quite simple and easy to understand that the wet temperature plays a 7 times greater role than the plain ambient temperature, and solar radiation also plays a very big role. So we can add this thing and we come up an overall WBGT temperature that represents everything. Of course, you don't have to have this type of device to do that. There are electronic devices that are commercially available that can do all these measurements and the calculation and automatically gives you the overall WBGT temperature. And some of those, they even have what is called an anemometer that can also measure the wind speed. Which is not part of this equation, but it gives you some idea of whether there is a wind, and that could also play a role on your ability to thermoregulate more effectively. So based on that, over the years, we have developed this type of scales that give you an idea based on the WBGT, what is the risk of the environment. So here you can see combinations between relative humidity and air temperature, and you can see different combinations. So for the exact same temperature, you could have an environment where the relative risk of being exposed to a heat injury is relatively small, while in other environmental humidity might be much higher. So in this example, let's take 90 degrees Fahrenheit or 30 degrees Celsius. If the relative humidity is around 20%, the risk is moderate, between low and moderate risk for heat injuries. However, if you keep the exact same temperature and you go to 85% humidity, automatically you're in a very high risk zone where it is recommended to either postpone or cancel a race, for example, for race directors. So fairly quickly you can see what is the important role that the relative humidity can play on the risk of cases of heat injury. And if you look in the epidemiology of exercise-induced heat stroke and associated deaths, you will see that most of them are results of very high humidity. So you will see much more frequency of this kind of terrible situations in places like Florida and south part of the United States versus places like Arizona or New Mexico, where the relative humidity seems to be significantly lower. So for the metabolic heat, I just wanted to show you one of the equations that we can use, and we can calculate metabolic heat production. And you can see one of the major determinant of metabolic heat production is the VO2, or how much oxygen we use. And the higher the VO2, the higher the metabolic heat production. So one of the things that I wanted you to make sure you understand when we try to figure out what is the main determinant of increase in body temperature and increase in sweating, for example, most people will think of the environmental conditions. Well, the appropriate answer actually is the exercise intensity. Exercise intensity, and more specifically, how much oxygen you use is the main factor that impacts how hot our body will get and how much we will sweat. Think of yourself standing in a cool, in a hot room, for example, and how much you're sweating versus exercising very intensively in a relatively cool environment. So standing in a hot environment, your body does not produce so much heat. Even though you might sweat, the sweating will be minimum, while if you're exercising, even in a cool environment, the high oxygen consumption leads to high metabolic heat production, and as a response, your body has the need to dissipate that extra heat. So exercise intensity and oxygen uptake is the main determinant of metabolic heat production, and as a response, heat load for the body and an amount of sweat that is produced. So if we look how our body dissipates heat in different conditions in rest, if you see those three slices, where actually, let me pull the next one so we can see the legend. The red represents the evaporation, the yellow represents convection, and the pink represents radiative heat loss. We see that at rest, most of the heat loss is driven primarily by radiation. So what is the temperature in the room and how much temperature we lose primarily by radiation. We don't really sweat that much that we will have a significant amount of sweat evaporation for heat dissipation at rest. On the other side, during exercise that you can see on the right diagram, you see that most of the heat dissipation, most of the heat loss is driven primarily through sweat evaporation, which, as we mentioned earlier, is the main and the most effective way to dissipate heat. Of course, this is a very generic approach. Somebody might think that, yes, that sounds reasonable. However, if the relative humidity suddenly goes to 90-95% humidity when it is raining and the temperature it's a little bit lower with exercise, but humidity is very high, then obviously the evaporation pathway, it can be completely blocked, so you don't really have so much heat dissipation via sweat evaporation. So just a quick reminder, I know we spoke about this diagram. Just to remind yourself, this is where sweat is produced. This is the fluid compartment that your body is using for sweat, the interstitial fluid or interstitial fluid volume. So when you sweat, you lose primarily water and less electrolytes, which is sweat is quite diluted actually. It's hypotonic, has low content of sodium and other electrolytes. So by losing mostly water than electrolytes, this compartment becomes more concentrated. So the tonicity in this compartment goes up, and through osmosis, you can pull fluids from the plasma and from the interstitial fluids to help maintain this volume. So before closing, I wanted to discuss a little bit some very old data. By now you might understand that I really like some of those old data. Those are from 1938, Bodil Nielsen, one of the scientists, one of the women that really influenced what we know today on temperature regulation and thermoregulation. This is one of the classic studies where she took subjects and they make them exercise in different workloads, from very light exercise, 350 kilogram meters per minute, which is less than 100 watts if you understand cycling intensity. And you can see how rectal temperature increases and stabilizes, and your temperature remains pretty much stable throughout this type of exercise. And the lesson that we can learn from this experiment was the higher the exercise intensity, the higher the core temperature. So during exercise, what happened, your body allows your temperature to increase and remain elevated all throughout exercise. This is not, of course, a case similar to fever, because your body knows that you have higher body temperature and it responds appropriately. It just allows temporarily for the temperature to remain elevated while you're exercising, and then after exercise the temperature will drop over time and will return back to normal. If you also see the same data together with sweating responses that you can see here on the top, you see that the sweating response is it increases in parallel to the increase of rectal temperature. So the higher the body temperature, the higher the sweat rate. So we already spoke on body temperatures from different areas, and you heard correctly the term rectal temperature, which is a temperature measured in the rectum with a flexible wire through which it can be placed in the rectum. We position it 10 centimeters beyond the anal sphincter, and it stays there all throughout the experiment. Of course, nowadays we've been using other techniques, which is a little bit easier to deal with and easier to convince subjects to participate in studies, like ingestible pills, where you have some type of internal temperature. We like to call it GI temperature, which is one of the index of that we can use to understand core temperature or real deep core body temperature. So throughout the years, we have been using rectal temperature, which is one that we just spoke about it. Esophageal temperature, which is a temperature measured with, again, with a flexible thermosensitive wire that goes from the nose down to the esophagus. And we position it in a spot which is very close to the pulmonary artery, so we have very high blood flow in this area. So it gives us a good idea of internal body temperature, and also it gives us some idea of rapid changes in body temperature. Over the years, we have used other spots like internal muscle temperature. So in active muscles, we can put sterile electrodes that are sensitive, and we can measure temperature. Tympanic temperature has been used in the past. It hasn't been very popular the last probably 20 to 30 years due to the discomfort and the inaccuracy. Ear canal or oral temperature with AU oral is a temperature that has been widely used just because it's very convenient, but it's not very accurate for exercise, especially in outdoor places. And skin temperature is something that, even though it doesn't represent core temperature, it gives us an idea of how heat flows from the core to the skin, and based on the difference between core to skin, we can make some calculations on temperature gradient and energy flow from the core to the environment. For the skin, of course, it's also a little bit complicated. The question is like, where do you measure skin temperature? This is one of the most commonly used formula, which is called the Ramanathan equation. It was published many, many years ago, back in '64. Different factors for chest, arm, thigh, and cuff. So you get two sections upper body, two factors lower body, and you get what is called the mean weighted skin temperature with this equation. A couple more things that you will see in this topic around temperature regulation, heat injuries, etc., is the skin blood flow. So we measure quite often skin blood flow to understand how your body regulates skin blood flow to allow good flow to the skin, so we can dissipate heat from the core to the environment. We can measure skin blood flow with different techniques. One of them, which is probably the most common and the most convenient, is via laser Doppler probes. That laser Doppler is positioned on the skin, and it measures speed of the red blood cells. We can also use laser scanners. I'll show you an image in a little bit. And also there is an older technique, it's called plethysmography, that it pretty much measures the volume, usually of your forearm, and based on changes on the volume, you can calculate changes in skin blood flow. This is an image that you get from the laser probe, and there are no real units for that. You get a flux that increases. You can express this data as % of maximum skin blood flow, usually to compare between different conditions. This is image of skin laser Doppler assessment, where you can use those scanners to have topographic assessment of different areas that vasoconstrict and vasodilate. And based on the color, you can estimate increase or decrease in skin blood flow. All right. So in closing, just I hope you enjoyed this lecture, and I hope you understand the pathways of heat exchange in different environments. Please make sure you understand those slides, particularly with the cyclist pictures and the different environments, and how different environments allow different mechanisms of heat pathway to be more active and less active, and how we can transfer heat in different environmental conditions based on temperature and humidity. Thank you.